And with that, I think I'm going to rest my voice. Next, I'd like to introduce Mike Plumb, the youngest member of this team. And Mike is the Director of Operations for Precision ERS. He's an expert in electronics repair. He has a BSEE from Tampa Technical Institute. I like little known facts. He's the Canadian, he's the Greek, I'm the Sicilian, and Carmine is from Queens, right? Queens, New York, so that's a different category. So, his personal interests are water, barley, hops, and politics. I'll leave it to you, Mike.
So while Martin's pulling up the presentation, I just wanted to start with saying how impressed I've been this week with all the talks and the presentations that we've listened to. You guys are working on these emerging technologies. You're working on these cutting edge technologies, these great innovations that are really going to truly, not just change our communications industry, but really change the way we all live our lives. I mean, we had a serious talk about Scarlett Johansson robots, so that's pretty incredible.
Oh, around the fire with lemonade in here, man?
No, that was here.
Oh, it okay, yeah. Continue later, so.
So, our group kind of came here to crash that party, so to speak. We're going to come and talk about the dirty, the ugly, the not at all glamorous world of legacy networks. The reality is that Mike mentioned that legacy networks do exist. They are a problem for operators. And with this presentation, hopefully we'll talk about some solutions. So Mike mentioned the bathtub curve. Everyone's seen this. I just thought it would be interesting to show what it would look like if we overlaid repair data from a repair house. So on the infant mortality state, we see that the number one problem for sure is solder-related issues. Interesting note, our data shows that over 20% of boards can be repaired just with solder reflow in this stage. The second stage would be the normal useful life. For sure, what we see far and away is transient voltages, power surges, lighting damage is the main factor for pieces coming into repair. And then when it gets to the end of life section, the biggest issue by far is component aging. Component aging is what's causing these units to come in for repair and what we're seeing. So I want to focus this talk on the two primary challenges when dealing with repairing legacy products. The first one is understanding component aging. You have to understand what components are susceptible to aging. Silicon components theoretically will last forever, most of them, but not all components are built like that. So you need to understand which ones don't. You need to be able to understand how to detect symptoms of aging and what to do about it. And those might not be failing the tests, so you have to understand what signs to look for. The other thing we see a lot in the industry today is operators are stockpiling out-of-service equipment for use as spares. And that works as a good strategy. I would say that it's a band-aid more than a solution because those operators haven't dealt with the component aging problem. They've saved money by avoiding repair, but how much does it cost to dispatch a technician to a fault? The other issue is obsolescence. So obsolescence is really the number one reason that most repair vendors are not able to successfully repair legacy equipment. We would say that with some creativity, a cost-effective and oftentimes more robust, because we've learned something about why the unit failed, can be developed. So I want to show you guys some data. So this is data that comes from a repair program that we're doing in Tampa for a legacy product, which is the DMS, Hotel DMS product that we're doing for the OEM in Tampa. So this just shows what types of components are being issued to repair orders really over the last 12 months in our operation. And obviously, there's no surprise that capacitors, aluminum electrolytic capacitors, overwhelmingly are what is being used and repaired in our operation. And then, in a very distant second, static memory is a factor. So, a little bit more about capacitors. It's not just a failed component. Capacitors, leakage, electrolyte leakage is a really big problem, and it needs to be understood by whoever's doing the repair. It really needs to be cleaned very thoroughly, and that's difficult to do. The electrolyte can be corrosive to the copper traces. It affects solderability, which therefore in turn affects conductivity, and really causes havoc in circuits, especially high current circuits. You can see all kinds of different results, intermittent results with poorly cleaned electrolyte. So electrical mechanical components, Mike mentioned that, fans. So most high-end fans used in the telecom world are rated for 60,000 operation hours. That's by the OEM. That's about 7 years. With proper care in a good environment, you can probably double that life. Low dust and humidity are the killers for fans. However, when mechanical components fail on fans, they can be repaired. You can replace the bearings, the impeller shaft, and even the impeller itself. SCSI drives are a huge problem right now in our industry. They're failing at an accelerated rate in these legacy networks. People might say that a 500 megabyte SCSI drive is an obsolete component. I think we would argue with that. There's definitely viable options to replace these older SCSI drives. The other thing to understand about SCSI is it's important not just to check whether the drive reads and writes data. You really need to check to make sure it's performing up to speed, the RPMs, and also if there's any mechanical noise or excess current draw with the drive, detect if it's aging. So when we were talking about content for this session with Chris, he said he wanted me to put a thermometer on this slide, so I did. But the key point here, obviously, is temperature is important in your networks. The FLIR image on the right shows that SRAM ICs operating very close to their upper threshold. Now, this was in our nice, clean, beautiful test lab in Tampa that has 70-degree ambient temperatures. You can imagine those temperatures were 10 or 15 degrees warmer. In theory, those ICs would be exceeding their temperature range. All right, so obsolescence. So Mike's slide is called Fight Obsolescence. So I call this one Fight Component Obsolescence. And the point here really is that, again, with creativity, cost-effective, robust solutions can be developed. There becomes an inevitable point in a life cycle, which Mike alluded to, where all support is ended, all spares are used up, and the service providers have a significant risk of an outage. At that point, they become very desperate and are willing to spend relatively large sums of money on a repair solution. And in that case, we can get very, very creative. So I did want to showcase a couple actual solutions that we've done for our customers, including ZT, on obsolescence. So this one is a SRAM solution. This is a very simple design. This is a Nortel DMS board that had an array of 16 64K by 1 SRAM ICs. Very hard to get, very old. So what we did was we built a drop-in-place printed circuit board on the right with a 64K by 8 SRAM IC, and it drops right in place to the removed ICs, and it works. Second solution is a optical module. This is on a Telabs Titan 5500 OC12 card. The original optical receiver on the left has a built-in clock receiver module. It's obsolete, not available to be purchased. So what we did was we built a PCB retrofit again with a separate clock recovery circuit and therefore we can use any commercially available CQR receiver that meets the specifications, and it can drop into place and work. And this last one is the one we did for ZT. You can see on the left what we typically see from the units coming in, other than this one that also happen to be dropped. The components, there's a heat dissipation area, and this is not just a component issue, the actual PCB is losing its dielectric properties. It's called for a complete redesign. So we reverse engineered a whole new board. It's a simple design, so we could do the reverse engineering fairly cost effectively and quickly. We use extra space that's available. You can see in the top right, there's extra space available. We added a fan. We also added ventilation holes and increased the width of the copper traces in many areas to allow heat dissipation. This is where we've learned where the failures of the components are and can build a more robust solution that's actually more cost effective probably than the original.
So the original's on the left.
The original's on the left with the burned MOSFETs and some resistors that are giving up the PCB. The finished product that you saw the video of us building is the new design. It's a larger board. The hole at the front is for the fan, and then the finished product, all assembled with the power supply, is so, just to wrap up, I think the points I'm trying to make are, legacy networks pose a real problem to network operators today, and they can be supported through repair operation with some creativity.